Now we're going to look at a new diagram. And remember, I'd like for you to print this out, take your colors, and color it in first before you watch the video. Now at first glance this doesn't look like too complicated of a diagram, and really it's not, but there are a couple things that are different that we're going to introduce. Now let's look at the rules we use in coloring these diagrams. Power and ground travel the path of continuity. Now they travel right through a coil because you know a coil does have continuity. And they stop traveling at an open, and power and ground change their value at a resistor. These are the rules that we're going to look at in this diagram. Now this example right here, or this symbol, is a resistor. It's a load, and a load consumes voltage. So now at the very bottom you look and you see we've got a dotted box. This is our ECM. It's a control unit, and again the dotted box means there's more in this control unit. We're only seeing what's necessary for this diagram. And this box up here is telling us that there are 3 connectors. Why is that important? Well, let's look at these 3 different connectors. You have connector 3, connector 2, connector 3, connector 2, and connector 3. Now if you're diagnosing and you were just trying to back probe the EGR, everything would be in connector 3. And if you were trying to back probe for testing purposes the idle air control, it would all be in connector 3 as well. But look at the TPS. The TPS has the middle wire coming out of connector 3 and has both of the end wires coming out of connector 2. And the same thing with the MAT sensor, the manifold temperature sensor. You would actually have to back probe connector 2 and connector 3 if you're testing these 2 units. Okay, so let's take a look at this diagram now. Let's color it and see what's going on, how it works. Now there are 5 devices in here. We have the MAT sensor, which is your manifold air temperature sensor. You have your TPS, your throttle position sensor. We have our idle air control valve. And you have your EGR. In this case, it's a digital EGR. And don't miss this one up in here. It's a device, it's a canister purge valve solenoid. Now the symbols in here, this one is a variable resistor. You see it in the manifold temperature sensor. It's a variable resistor. Now this is what a variable resistor would look like. It's an air temperature sensor. There are 2 wires. You can see the 2 pins, and the connectors are 2 pins. Now you can see our 2 wires, a black with pink and a black with red. There's the 2 wires for the manifold temperature sensor. Now the next one is a potentiometer. We've already looked at that. It's the TPS, and it is a variable resistor, but it has a sweep component or a sweep feature to it. And you look down here, it is a 3 wire. Where the air temperature sensor was just a 2 wire, now we've got 3 wires. Now if you look at just kind of a graphic of this, you see that you've got 3 terminals or 3 wires. The middle one is tied to the sweep feature, and the other ones are continuity through the sensor itself. And here's some examples. They can look different by the different makes, but they all basically are going to function the same. Now over here on the right we have a solenoid. This is the symbol for a solenoid. And in the EGR, the digital EGR, you can see that we've got solenoid A, B, and C. And each one has its own control. Now this is a 4-wire sensor, 3 controls and 1 feed wire. Here's a digital EGR. There's actually 3 solenoids inside this thing. And as we look at the exploded diagram of it, or the illustration, you can see the 3 solenoids and the armatures are inside. Now another solenoid is the canister purge solenoid valve. Notice that it is just a 2-wire. Now these purge solenoids can look a lot different based on the car that they're in, but if you look, they're all just 2 wires. You can see it in the connector here. They're going to look different, but they all do the same thing. They just open and close a valve. Now also another symbol is for a motor. You can see it right here. Now this is a bidirectional motor. We've got a winding on both sides. Now this is an idle air control motor. This is for a Ford, and if you look inside here you can see that there's 4 pins. An idle air control is a 4-pin device. Now our power, as it says up there, is hot and run. So the fuse gets its power when the ignition switch is switched to the run, the bulb test, or the start position. Now I want you to notice on this diagram where the power comes from. We colored that orange because it is switched on. But if you look real close, the power comes down and it goes right through the canister purge and it comes over to the EGR. But there is no fused power to the idle air control, the TPS, or the air temperature sensor. There's also, this goes over to another fuse diagram. But notice, of the 5 devices, only 2 of them have direct fused power. Now we have some grounds. Now this is inside the ECM. The ECM has a ground, but it feeds the EGR through 3 separate grounds. Kind of like a small, medium, or large. That's what I like to call it, because as it operates, it's going to give you a little bit, kind of a medium amount, or a large amount. So when the PCM commands this ground signal, the solenoid A will open and allow a little bit or a small amount of EGR gas to flow. And then when the ECM commands the middle solenoid, it opens and it adds to what was already open in the A solenoid, and so you kind of have a medium amount of EGR gas. And then if the ECM determines that we need maximum amount of EGR gas, it actually grounds and opens up the 3rd solenoid. When you add all 3 together, we've got a large amount of EGR gas. Now again, this is fused power. Now let's look at the canister purge, because it's the only other one that has fused power. It comes down and it stops at an open. It has a ground inside the ECM, and when the ECM grounds that switch, then it goes up and the canister purge will open because it has power and ground. Power on the top side, fused power, and switched ground. When you have power and ground, the device will operate. Now let's look at the idle air control valve. If you notice, the idle air control does not have fused power, but where does it get its power? It has to get it somewhere. If we look down inside the PCM, you'll see 4 battery feeds. That means 12 volts, or system voltage. So we got 4 system voltage, and you got 4 wires. But you only have 3 grounds. So obviously this one right here is going to share this ground connection, the one in the middle. Now I want you to notice over here this dashed line. There's one here and there's one on the left side. Now that dashed line means this switch and this switch are going to operate at the same time. When one moves, so will the other one. And then likewise on this side, when one moves, so will the other one. So what does this symbol right here mean? It's a pulse width modulated, or square wave, or in other words, it's going to be pulsed on and off, on and off, on and off. So the idle air control doesn't just boom get full power, it's pulsed on so that it can open up faster or slower depending on what the need is. So if we need the idle air control to run in one direction, these two are switched together. So this will switch to ground and this one will switch to power. You've got power on one side of the motor, ground on the other, so the motor will run. It'll run in one direction. If we want the motor to run in the other direction, we're going to have to switch our power and ground. So that's why these two then will operate. Now this one closes and it switches to ground. Notice that that moves the same when this one does, and this one closes and it moves to power. So you have power on the top, ground on the bottom, and the motor will run in the opposite direction. Okay, so let's look over here now at the TPS and the air temperature sensor. If you look right here, there's a ground that's going to be shared by these sensors. So when the PCM grounds this, it comes over and gives a ground to the air temperature sensor, and it gives a ground to the TPS. There's a resistor, so the signal will actually change right there, so that's where we stop coloring it, showing that it's changed. So we've got one ground shared by two sensors. Now these sensors do not have fused power, so we're going to have to find the power. In the middle right here on the TPS we have another ground. Now notice the ground is switched on, but it stops at a resistor or changes its value at that resistor. But where do we get our power? Well, right next door you see we've got a 5-volt reference that is supplied by the PCM. So when the PCM gives it ground and gives it a 5-volt reference, that reference is going to travel and go up to the other side of the resistor. Now a potentiometer is a sweep device or a rotating device. As it rotates, the indicator will move, and it'll move one way showing less resistance, and then it can sweep across the other direction showing more resistance. But as that resistance changes, it then travels down this wire and it actually reports to the PCM the TPS input. A variable resistor, since it's a varying resistance, it's a varying voltage drop which is reported to the PCM through the input. Now let's look at the manifold sensor. It's got a 5-volt reference from the PCM, so it is going to travel until it reaches a resistor, and then it's going to change its value. Now it's got power side here, it's 5 volts, and it already had the ground, because remember we had the ground shared. So what goes in between? That's the signal wire. As the air temperature sensor heats up or cools down, this resistance value is going to change. You have ground on one side and you have power on the other side, so the resistance changes on this wire and it comes in and becomes the input into the PCM. The TPS, it's actually going to have a power, a ground, and a reporting wire because it is a different type of variable resistor. Now this sometimes can be a little bit confusing, so let me try to explain it in a different way. Let's explore these rules for a minute. Power and ground follow the path of continuity. Power and ground stop at an open, and power and ground change their value when they reach a resistor. A load is a resistor, and it consumes voltage to accomplish work. If we take a 12-volt battery and we hook up a load to it, and that load is a light, then the work we accomplish is a light, a bulb. Now if we take another load, which is a motor, and we hook that up to power and ground, the work we accomplish is the motor runs. If we attach this wire to the battery, after all the wire is a resistor, and we touch it to the positive post, what work are we going to accomplish? Well, I'm not so sure it was work unless you're talking about welding, but we actually fried the wire. That's not good in a car system. That's why we protect our circuits with fuses rather than risk smoking wires. So why did the wire melt? Because we've got 12 volts too much voltage for this resistor. These resistors were okay. Now let's back this up a little bit. So if our battery delivers 12 volts and the alternator more than that, we've got to be able to bring that down to make some of these electronics work. So if I take just a regular old 6-volt battery, that means the most it can deliver is 6 volts, and I set that up here, and I take my same load for the light and I hook my wires to it. That load barely works, but it's a lot dimmer. Now if I take my motor and I hook my motor up to 6 volts, if you look at it, it struggles to run. Now if I take this resistor, which is just a piece of wire, and I hook it up to the 6-volt battery, it doesn't melt. doesn't smoke, doesn't spark. But because it is hooked up, there's continuity, current can run through it. Now if I take this wire, which has multiple strands in it, and I cut it apart and I want just one strand out of there. Now if we take this single strand of wire, and wire, you know, is a resistor, if we hook it around the battery, the 6-volt battery, it doesn't melt, but current can flow through it. Now if we were to interrupt this circuit and install a variable resistor like a potentiometer in between it, it would have power and ground on one side, but as we rotate it for the potentiometer, we would see the resistance value change, the voltage drop would change, and we could measure that on that third wire. Now if we actually installed a thermistor, it is a variable resistor as well, but it doesn't vary because we can sweep it. It varies it as the temperature rises and falls. But if we install this in that circuit as well, we can monitor that voltage drop as the temperature rises and falls and changes the resistance value. That's one of the reasons we use a 5-volt reference, because current can run through it, but as the resistance changes, we can measure it.